Hey there. Everybody, my face is blocked by a Global Hack Week sign. But yeah, hi, how are you? I hope you're doing well and enjoying your Global Hack Week. Welcome. Maybe if there's anyone in the chat who can just give me a little sign of life down there, please let me know. Um, okay. Hi, Stephen. Hi, Pep Zero. Oh, maybe you like Pepsi Zero, or maybe Penguins. But either way, good to see you. And hi, King of Books, and hi, Quackers and Cheese. I love all of your names today. Uh, Very creative. But yeah. So anyway, we're going to be talking a little bit about what are LLMs today. But before we get started, I want to make sure that all of you are able to check in for the event. So I'm going to send around a link, and this is going to be a link to check in. And just quickly send that over. All right, this should be it right here. And it's going to help us because we love to see what people are interested in, and what kinds of content you like to see. So this is one way we can help know that. And on your side, it helps you get points for your Global Hack Week. So definitely go ahead and check in. Okay. So before we get started, um, well, actually, let me go ahead and share my slides with you now. Let's see. There they are. So we're going to create laptop LLMs. And what I mean by that is we're going to start from scratch and build some algorithms that are essentially going to mimic what you see in ChatGPT and some of these largest models, but we're going to build it on our own. And of course, it's not going to be quite as impressive, but for us, it'll be really impressive because we're going to use so much less compute power. Okay. But I'm Steven, and I would love to know a little bit about you all. And so I sometimes ask folks if they're comfortable to introduce themselves. So if you could just give me a first name or greeting. Otherwise, I'll just use your username to greet you. And then which country are you logging on from today? So if you feel comfortable, let us know, because I love to see how global our community is. And then finally, what do you want to learn today? All right. That's going to be a big part of this workshop. All right. Hi, Harshita. Good to meet you. I'm logging in all the way from India. Amazing. I'll just go as well. I'm Steven, and I'm logging in from California. And yeah, I'm really excited to learn a little bit about LLMs, because it's become a very popular thing lately, and maybe you find yourself using the technology but not knowing how it works at the basic level. Hi, Gabriel. Good to meet you. And all the way from Brazil. And I guess in Brazil, it's the summertime. I kind of wish it was the summertime here. And Aryan from India, and someone from the US, Quackers and Cheese from the US. I want to learn the basics of LLM. So that's great. Thank you all for introducing yourself. It's really good to get to know each other a little bit better. But here's what we're going to do. As I said, the goal is really to demystify the process of creating a basic language model. We want to focus on some of the fundamental concepts and ensuring that we get those right. Okay, so I have a little I guess, agenda for the day. And I'm honestly not sure if we will get to all of it. But if we don't, we have several other sessions planned throughout the week. So we can go during those and continue on this. All right. But the idea is going to be to first discuss the foundational concepts of large language model. Then we're going to set up our environment, ensure our laptop is ready. And I'm actually going to use Google Colab, which is one of many subscriptions to subscription services. The reason I'm going to use it is because I want to be able to share with you a working version of our project together. So be on the lookout for that. And then as far as data preparation and tokenization goes, we'll also learn how to prepare our text data. If you've never heard of tokenization, it's basically how we can break down the words into subwords that make it easier for the model to understand, because it will have then more training data, because you're sort of artificially augmenting the training data. And of course, questions are welcome, some interactive participation. And actually, I decided to do this on Google Colab, not GitHub. So sorry for the error, the mistake there in the slides. But here I'm going to drop a link to the Colab that I will just keep updating over the course of the workshop. All right, here it is. And we had a request also to share the slides, so I'll do that too. Let me just share those slides with you too. Here is this. All right, let's go back. Just a question in the chat. What is a laptop LLM? The idea behind a laptop LLM is that you're going to be able to work on this yourself, run this from your own computer. So yeah, we will definitely get more into detail on that. But yeah, okay, let's go back to where we were. All right, so now hopefully the GitHub is shared with all of you, or in this case, our Colab notebook. And we're going to be live updating that over the course of the time, but you're welcome to make your own copy of it and code along, or you're welcome to use your laptop itself. And this is the link to the slides. All right. Great. So first, we're going to set the context and just understand what are LLMs. So they are a system that predicts the next word, or specifically the next token, in a sequence-based model based on the input that is received. And what does that mean? So for example, if I said to you, hello, how are, and the last word, you can be pretty sure it would be you. And you use context to get that. And the LLM is just always looking for that next word and what is the most likely next word. And modern LLMs are built on the transformer architecture and have transformed applications in a field called NLP. Okay, so NLP used to be somewhat of a small field, but now it is just becoming so transformed by these LLMs and widespread adoption. Yeah, and a really good question here. How is it then that the LLM can do math if all it does is predict the next word? That's a great question. So I guess you're getting at a really important idea here, which is that just by predicting the next word, there are emergent properties of the LLMs. So just by predicting the next word, people have found out that they can do mathematics, that they can do other things. But with math in particular, it's kind of a special domain with lots of constraints. So they may supplement training of LLMs with a transformer using some other kind of learning and not just necessarily predicting the next word based on a large portion of text, but they might actually use reinforcement learning to coerce the model to actually learn more math related concepts and increase its training capacity. But that's a really good question. Exactly, like supervised reinforcement. All right, so here's a few realistic expectations, and this is more about Pep Zero's comment where, what is a laptop LLM? Of course, to build a full-scale LLM requires so much computer resources. I think actually that now they're talking about building a $10 billion model. But we don't have that much money for this workshop, unfortunately. So we're going to build a simple version that runs on your laptop. Okay, so for everyone, you must have the following. And if you don't have this, this first bullet point, you can use a Google Colab notebook, like the one that I shared. That's totally acceptable. But whatever you use should have some sort of Python installation. And I sometimes recommend Anaconda, which is a great way to manage your dependencies, and some pre-installed libraries. So there's just a few off the top here that I thought of that might be helpful for this workshop. PyTorch, TensorFlow, Transformers, NumPy. But we'll go through the workshop and we can install them over the course of the workshop. All right. So I wanted to take a second, a breath. Does anybody have any questions so far? I've seen a lot of great questions in the chat, actually. But if you have one, now is a good time. And Leo, hi there. Good to meet you. Got a few folks joining. And I see some familiar faces and also some new faces to our community. So welcome. Yeah, how was everyone's weekend? I hope you got a good, got up to some fun, or you got a good rest. So this depends on if you are going to be using GPU and using CUDA. We're probably not going to get into CUDA, things that need CUDA for this today. But if you want to use a GPU, you probably will need CUDA. All right. So we'll go ahead and continue on. But here's an icebreaker question. What's one cool application of AI that you're excited about in the future? So I wanted to put that out there because while we're thinking about any questions, it's good to have some icebreakers. So maybe you could just tell me about that. I'll tell you. One thing I'm really excited about is the use of AI in robotics. I saw some hackathon projects this last weekend. We were at Tartan Hacks, which is a Carnegie Mellon hackathon. And they had some really cool robotics hacks. And one of them was using an arm that was powered by ChatGPT that could actually feed a patient their food in the hospital or in the rehabilitation clinic. So I thought that was really cool. Does anybody else want to share what they thought was a cool application of AI? AI is becoming world leaders. Incredible. Yeah, I think it's actually somewhat possible that you could have rational actors like AI become more useful in society. That could be really cool. And research into archaeological data. That's very interesting. Yeah, I've seen a lot of I don't know if you've seen these, but they take a satellite image of the forest, like the rainforest, and they can, or the mountains, and they can look sometimes for um, old symbols that were left there. In Peru, I think they do that. Yes, satellite image parsing. So it's a really cool field. But all right, so we're going to start then on what is a language model. So we already said about this. It's telling you about what is the most likely next word, but it's doing that through probability. Okay, so it's going to assign a probability to a sequence of words to tell you how likely it will be that a given sequence of text is going to occur in a language. So it's essentially building a giant probability matrix of the language that you're learning, that it's learning. And what can it do? Well, a lot of you might already know this, but large language models can predict the next word, yes, like the cat sat on the mat or something like that. But they can also generate coherent text that seems human-like. And people have used them for other things like translation, summarization, and question answer. But the basic idea behind them is the chain rule. So you might have heard of the chain rule, and it's basically saying that the probability of some event happening is the product of all of its conditional probabilities. So if I had a sentence like the cat sat on the mat, how many words is that? The cat sat on the mat. That's 6 words. And so we could say the probability of those 6 words occurring in that order is P W1, W2, W3, W4, W5, W6. So P cat sat, the cat sat on the mat. And then we have to multiply all the conditional probabilities. So we could say probability 1 is what's the probability of cat, given that the is the first word, and so on. And then we would have some probability of that sentence. A few more here. Advanced literary editing. That would be cool. Yeah, another hackathon project I saw was trying to help readers get tailor-made content from their favorite writers using LLMs. And DatFab0 says it does the same thing for images, I think. Yeah, so there's something called Vision Transformer. And Vision Transformer, in that case, tokens are actually patches. And we're going to discuss Vision Transformer this week. So stay tuned if you're interested in that. And so an LLM wouldn't be able to produce something completely different from its data set. Yeah, that's true. So there's no magic sauce underneath it. It's really just predicting the next word from a set of probabilities. And so it can't invent a new word. Well, it can't invent a new token, I should say. I guess it could invent a new word, but it can't invent a new token. It's just going to predict whatever the next token is. Now, that being said, it could create some sentence that is not in its original data set, but that sentence would be a result of learning from the previous possibilities. And then the dude Lols says it would be very useful if you have recordings. We do. We have recordings of all our workshops available on YouTube. So definitely check that out. But we're going to actually do now an interactive example because I feel like I've been talking for a long time. And so why don't we do that? Amit, I love your question, text generation from image. But I think I'm actually probably not the best person to ask about that because I haven't really done that. But if you did break in the image into, you could use Vision Transformer, for example, to break the image into tokens and then build a separate model that could actually handle that. But yeah, I'm not sure. That's a good question. But today we're going to do something a little bit more simple, which is a simple chain rule. Okay, and we're going to compute the probability of a simple three-word sentence, and we're going to use our workshop codes to do this. Okay, so I'm going to give you all a function in our code. Here's the tab, and it doesn't rely on any libraries. It just relies on Python. So as long as you have Python, you'll be able to do this. Let me make this a little bit, bigger. But check out this probability function, okay? And it gives us the probability of a word in its context. So you can see PW1 is just 0.5. According to these probabilities that are just learned. We're not sure how they got learned, but just telling you, this is what we learned. Probability W2 given the letter hello. So I said hello, and then given that is 0.3. And then finally, if you say hello world, the probability of saying again is just 0.2. So if we say hello, we might not say hello world. That's only 1/3 of the time that people would say hello world. And then, or almost 1/3. And then hello world again is even rarer. So of all the people who said hello world, just 1 in 5 said hello world again. Right? So based on this, let's do an example sentence. Which is hello world again. Kind of a rare one. A good question. Do all of the probabilities have to add up to 1? I noticed that the one example here, they do add up to 1. But no, they don't have to add up to 1. And the reason is because these are conditional probabilities. So they're not all part of, these are not all the possibilities, right? You could say, hello, it's Kokopo, right? You could say, hello, image generator, whatever you want to say. So they don't have to add up to 1, but that's a very good question. So thank you for that. And actually, let's see here. All right. So we're going to move on now and actually get to computing this probability. So we're going to compute probability. All right. So we'll take words. So the first probability is just P0, or P1, PW1, sorry. So PW1 is not given anything, right? So we can just put some blank empty pair here so that it goes to here. And then we're going to multiply by the probability of word 1. And remember, this is just the chain rule. Given, of course, word 0. So this is the part where we multiply by PW2, given W1. And then finally, we're going to do PW3, given W2, given W1. So that will be probability of words 2. I realize this is getting quite long. You can just imagine, how does the LLM keep track of all this, right? It's a lot to keep track of. And then we'll print out the probability. Oh, see, there it fills it in for me. How great is that? So this is what we call the joint probability of the sentence. I'll write that too, actually. Oh, it didn't actually finish. It's work there. Sometimes they finish on their own and sometimes they don't. Error, yeah, definitely an error because yeah, thank you. Yeah, some so even these things, they're not super smart. you still need you to fix their problem sometimes. Yeah. So okay. Yeah. So it's got the error. So let's just run it one more time. Oh, I never gave a words list. Sorry, I put a words list in my original code. Okay, there must be an error here somewhere. Oh, more parentheses that I forgot to close. Silly me. Okay, so the joint probability for all of these is quite low, as you can see. And the reason is because you will not see this sentence all the time, right? So you have to take that into account. The LLM is speechless, yes. All right, so it's not, so this is like, you could say this would be the probability of just finding this sentence out in the wild, finding it out in like Wikipedia, for example. And then, we can continue the sentence, and all of the other sentences that branch off of this are contained within here. But we could get even further. We could get hello again, Paul, and we could just keep going with it. But that's the basic idea of how these simple chain rule methods work. All right. But that's not all we have for today. I wanted to talk a little bit about language models as an overall history. Okay. So first, I wanted to talk about statistical models. So this is essentially what the field started as. And remember, I told you, natural language processing has been around for a very long time, but it wasn't always such a famous field. And back in the early days, there were things called n-gram models that you might not have heard of. And these predict the next word based on the previous n-1 words. So we actually could just create an n-gram, a 3-gram model, where we say hello world, and the goal is to predict that last word again. But it requires 2 words to start. And the problem is they have a lot of data sparsity, So what that means is that you can't really get a lot of different possibilities from just a 3-gram model. And they also have limited context. So yeah, if I just told you 2 words like brown chair, that doesn't give you much context at all to predict the next word. So even though they were a great first step in this domain, there was a lot of problems with that. And so, yeah, I told you 2-gram, 3-gram, so on. And then here's another model that's very popular. This is still has a lot of applications today. They're called RNNs, which are recurrent neural networks, and LSTMs, which are long short-term memory, I believe is the algorithm. Um, I always forget that one. Yeah, long short-term memory, which is just like a very specific type of RNN. But they're both current networks. Process sequences in order. So what I mean by that is they are paying attention to a certain context window in the sentence. Okay, so it's just like the 3-gram and the 2-gram, although they can weight their different words and process them as they go along in the sentence, right? So they can have some sort of attention filter there. But they struggle with long range dependencies because they have a certain context window. And if the information is outside of that context window, it's not going to work out okay. They're going to need uh, some other architecture. And that's where the transformers come in. And that's introduced in a long-term paper, a landmark paper. Attention is all you need. This is what really introduced the transformers to the community of natural language processing, large language model researchers. And transformers, they rely on self-attention to process sequences in parallel and capture relationships across the entire set. So now we're actually going to look at all of the different elements of the sentence all at the same time, instead of just looking at some fixed context window. And so we're going to talk about some of the core concepts that underlie these transformers. That's really what we're going to talk about. The Geoffrey Hinton, I don't believe he was one of the authors of that paper. Don't quote me on that. But Geoffrey Hinton, he was one of these early researchers working on neural networks. So he would have known about all of these different types of neural networks, not just transformers, but yeah. Okay. So that's what we're going to do now, Amit, is elaborate on transformers. We're going to go into a deep dive of the different components and how they work. But I just want to answer some questions first. One of them is, how long do you estimate it might take to realistically build their own laptop LLM with strong, intricate context? Or is that not possible for very detailed contexts? So, yeah, I mean, that's a good question. I've heard, honestly, I mean, there's new information in the field where these companies like DeepSeek claim to build a really cheap model. And I have heard even claims that people have trained their own LLMs, excuse me, with just about $50 and get a really intricate LLM. And if that's the case, then you could do that on your laptop. But I will say a lot of those methods are relying on some form of pre-training or model distillation, um, which is not coding it from scratch. Okay, it's relying on a big model like ChatGPT, and then building off of that to generate your own model in a faster way, in a more efficient way. To do it in this way, where we're actually going to go from the ground up with transformers, it's really not possible realistically to build your laptop LLM with strong, intricate context. Um, so yeah, that would be kind of tough. But yeah, like Pep Zero said, it's based on your hardware power. All right. So first, we're going to talk about tokenization. This is the first example here, and tokenization is the process of breaking text into smaller subunits called tokens. And we are going to do an interactive example to show how this works, because it's kind of a strange concept to a lot of people. And so hopefully this example will help us learn more about it. So first we need to install transformers. As I mentioned, we're going to need to install a lot of things. So we'll type pip install transformers. And the reason we're installing this is because we're going to install a tokenizer, a pre-trained tokenizer from BERT. I don't know if any of you have heard of BERT, but that's one of these major large language models. And then, interesting, a chocolate pizza. That's cool. Maybe you could tell me a little. I'm very curious about that. I would love to know what you mean by that. But yeah, so let's go ahead and write this code. So from transformers, we're going to let's make sure we got transformers first by running a simple import statement, which should confirm that transformers is downloaded. Taking kind of a long time, honestly. Okay, and it did import, which means that it was successful. And now we can load some pre-trained tokenizer. Okay, so I'm going to say tokenizer. And we'll use the auto tokenizer from pre-trained. And yeah, why don't we just use this one that they have here? This one that they have here suggested. Okay, of course it's Gemini, so it's going to suggest BERT. Just kidding, but yeah. So let's get some sample text. Okay, so I'm going to give this one here. And does anyone know what is so special about this sentence? Does anybody know what's so special about this sentence? The quick brown fox jumps over the lazy dog. It is. It's classic learning to type and keyboard testing. Yeah. But I just thought maybe this is a good one. Yeah, because the reason is right, because as Joro says, it has all the alphabets. It has it has the whole alphabet in it. Okay. So now I'm going to tokenize this text. So we would understand this text as the quick brown fox jumps over the lazy dog. But the LLM needs tokens. So let's make a new variable called tokens. And we're going to use tokenizer.tokenize. And it's suggesting to print the token. So I like that idea too. So here's the tokenization. You can see each of the words has been broken up into its own token. Some tokens are seen twice, like the. You'll notice that this capitalization didn't translate here. But now we're going to convert these tokens into their corresponding IDs. Okay, so these are numerical representations. So we're going to take our tokens and we're going to call them tokens IDs, or token IDs actually. And we're going to use tokenizer dot convert tokens to IDs and accept tokens as the argument. And now you can see that the tokens are actually integer values. And so the LLM is understanding a period here. And the word quick here, 4248. So that goes to your question. Does it I see it tokenizes punctuation and words. Yes, it does. And I see no reason why you could not also put spaces. I think the problem though with spaces is it would be quite boring, maybe, because there's always a space in between different tokens. So I think space is sort of implied by your sentence, but there could be situations where you want to actually tokenize the space too. Like, for example, let's think about this. It's Kokopo. Let's think about this, okay? If I told you the, okay, that's your first word, the. What's the probability that there's a space, right? Ah, good point. There could be a period, right? So if I tell you my first word is the, what's the probability that and I'm also tell you that there's no punctuation. What's the probability that there's a space? So if there's no punctuation, there probably would be a space. So I think it's sort of inferred here, and just sort of inferred that if there's no punctuation, if you're not going to put a punctuation, then there's a space. But I guess you could theoretically put them in, because maybe sometimes people might put two spaces instead of one, or have some reason for wanting tokenized spaces. So that would be really interesting to look into. But that's a really good question, because as you said, there are situations where you don't have a space. Okay, so let's keep going, and we can continue along with our components of a transformer into embeddings. Okay, so embeddings are vector representations of tokens, and they capture the semantic meanings of tokens. And so what I mean by that is that words with a similar meaning will have a similar embedding. All right, so let's create an embedding layer with PyTorch. We're going to do an interactive example there. And so let's go ahead and do this. So PyTorch, give a message, give a chat if you've used this before, PyTorch. It's a great library because it has all of these incredible modules for programming machine learning algorithms. One of them is this .nn, which stands for neural network. You see, yeah, .pep0 has used it. Awesome. Yeah, neural network is great for building these complex transformer architecture and other architectures you might be interested in. So it's great to have that already there. And we're going to assume some small vocabulary size. So we're just going to give the model 1,000 possible words. And then we're going to give it an embedding dimension. of 64. Does anyone know that what an embedding dimension is? Because maybe you've used PyTorch. I'm not sure, though, if you know about what the embedding dimension represents. And while we're getting an answer, I'm going to put the embedding layer, okay, which is one of the key types of layers that we see in the transformer. Converts words to numbers. Yeah, exactly. So we're just saying that we have 1,000 words, but we want to reduce the information content of those words to just 64 unique numbers, essentially. And then this is interesting. Use stemming and lemmatization. I didn't even know that. But yes. So we're condensing the information. And so let's just imagine that our tokenized text is represented by these following tokens, okay? So I'm just going to give us some tokens to look at. Hi there, 404. Good to see you. Welcome to the stream. I'm doing good. Just got back from the Carnegie Mellon Tartan Hacks. That was a really great event. But now we're just looking at some random tokens, and we can pass those into the embedding layer and print the embeddings themselves. So let's take a look. All right. So we have now our embeddings. And again, the embeddings are telling us essentially how similar the words are to each other. So we have these 4 different tokens, which could be represented by different words. And these numbers are similar to the similarity score. Okay. So this is very key. And Templario has a really good analogy, I would say, here, which is like extracting features from your model. I like that analogy. It's sort of like extracting features. But in this case, we're looking for all of the relationships. So we're not extracting just the most important ones and throwing away the rest. We're going to keep everything, basically, right? So, all right, folks, unfortunately, we're going to have to leave it here for now because we have our Today in Global Hack Week stream coming up. And we're going to be having to do that. Yeah, so glad that you all were able to join. Actually, I just checked my messages and someone else. So it's going to be me and Cecilia who will be doing Today in Global Hack Week. Cecilia, it seems like, might be able to send the announcement for Global Hack Week, Today in Global Hack Week. So maybe we can do one more concept, because then we can wrap up this part where we talk about the transformer concepts, okay? And that's context and sequence modeling, all right? Just wanted to mention this to you. We don't have any interactive example here, but large language models need to understand context. And this is sort of like what we were saying with the embedding dimensions. Because we need to make sure that all of the dependencies in the sentence, not just a few or some rolling window But these modern architectures, like the transformers, can capture a super long dependencies. And has anyone heard of the term context window? Do you know what is the largest context window in these? Let's see, Claude, maybe. What is Claude's context window? Let's look at this. I'm really curious myself. Okay, so the context window for Claude Pro, if you buy Claude Pro from them, is 200,000 plus tokens. So that's about 500 pages of text or 100 images. So you could pass 500 pages of text to Claude Pro, and it would actually understand that. This is amazing. And yeah, I really want to learn about the chocolate pizza a little bit more. Um, maybe we can talk about that at the next one. But yeah, that's why GPT. Yeah, GPT is a little bit limited, actually. Yeah, there's no way for it to know about things outside of its context window. And yeah, it could only generate so much words because the same way. And yeah, as 404 mentions, we did a little history of NLPs at the beginning of the stream and talked a little bit about engrams and recurrent neural network and LSTM. And yeah, there's a lot of really cool stuff going on with those. But yeah, you missed, unfortunately, a little history of that. But I think it's really neat too. And yeah, but okay. So folks, oh, and Pep Zero says Gemini 1.5 Pro. I wonder what the context window of Gemini 1.5 Pro is. Okay, unfortunately, not as impressive. I think they said, oh, wait, actually, look at this. 1.5 has 1 million tokens. Goodness gracious. Okay, so if 200,000 is 500 pages, that means that this is 2,500 pages context. That's enormous. I think you could probably put an entire book or an entire textbook into the context window. Wow. Cool. All right, folks. So that's about context. And next time, we're going to do a deeper dive into the transformer architecture. All right. And we're going to get that. Yeah, 500 photos. True. And we're going to get that going. But for now, we're going to actually have to split because we have the Today in Global Hack Week coming up. All right. So I'm going to have to say goodbye to you all for about 5 minutes, but stay tuned, stay here, because in 5 minutes, we're going to have our Today in Global Hack Week, and you can learn about all the amazing streams that are going on. And I'm actually going to send you a check-in link for that stream. Paste it in. Thanks. It's Coco Pope. Thank you. It was really a pleasure to have you all in the chat and to have all of you here. It's not fun if there's no community around our streams, and you all are what bring the community aspect. So that's why these streams can be fun. Thanks, everyone. And yes, if you want to connect on LinkedIn, sometimes people do ask me, "Hey, can we connect on LinkedIn?" I'm totally happy to do that. And I'll send my LinkedIn in the chat too. I'll check that. Sometimes it takes me a little while to check LinkedIn, so I'll just give it a check after the streams. But all right, everybody, take care. See you soon.